Binary search is one of those rare algorithms that is both simple and deep. On the surface, it just finds a value in a sorted array. But under the hood, it teaches a far more general idea. Once the search space has a reliable order, every comparison can destroy half of the remaining uncertainty. That is a dramatic kind of progress. If you had 1 million sorted items, a linear scan might need to inspect all 1 million. Binary search needs only about 20 comparisons. In this lesson, we will not stop at the textbook version. We will build the mental model, trace a full example, study loop invariants, cover first and last occurrence variants, extend the idea to searching on the answer, and then finish with the bugs and edge cases that make this tiny algorithm famous among programmers. The first requirement is non-negotiable. Binary search needs order. Usually that means a sorted array, but more generally it means a search space where one comparison tells you which side can be discarded. Imagine a sorted shelf of values. You check the middle. If the target is smaller than the middle value, then everything to the right is useless. If the target is larger, everything to the left is useless. That single observation is the engine of the algorithm. Another way to say it is this: we repeatedly halve the portion of the search space that could still contain answer. Invariant-based thinking says the same thing more formally. We maintain an active interval and shrink it until only the answer region remains. The power is not magic. It comes from preserving certainty about where the answer can still live. Let us walk through a concrete search. Suppose the sorted array is 4, 8, 15, 16, 23, 42, 50, 57, 73, 91, 104, 120. Our target is 73. We start with low at the first index and high at the last. The midpoint lands near the center on 42. Since 73 is larger, the entire left half including 42 is eliminated. Now low jumps right. The new middle is 91. This time the target is smaller, so the right side disappears. One more midpoint lands on 57, still too small, so low moves again. The next midpoint is 73. Found. Notice what made the trace feel clean. At every step, the candidate interval got strictly smaller, and every eliminated region stayed eliminated forever. The strongest way to understand binary search is through its invariant. An invariant is a statement that remains true every time the loop begins. For classic binary search, the invariant is: if the target exists, then it is somewhere between low and high inclusive. Every update must preserve that fact. If the midpoint is too small, moving low to mid plus 1 is safe, because neither mid nor anything left of it can possibly hold the target. If the midpoint is too large, moving high to mid minus 1 is safe for the symmetric reason. This is why binary search feels unforgiving. If your update rule fails to preserve the invariant, the algorithm can skip the answer or loop forever. The comparisons are easy. The discipline is in proving that each pointer move keeps the promise intact. Here is the implementation mindset to keep. Use clear bounds, compute the midpoint safely, compare once, and guarantee progress. A standard iterative template uses while low is less than or equal to high. Inside the loop, compute mid as low plus high minus low divided by 2. That form avoids the classic overflow bug that Joshua Block documented at Google in 2006, where low plus high could exceed the integer range in very large arrays. Then compare numsmid to the target. If equal, return mid. If numsmid is smaller, move low to mid plus 1. Otherwise, move high to mid minus 1. When the loop ends, the target is absent. The code is short, but every symbol carries meaning. Bounds define the candidate interval. Mid samples it. Updates preserve the invariant and force the interval to shrink. Now let us go one level deeper. Often the goal is not to find any occurrence of a value, but the first occurrence, the last occurrence, or the insertion position where a value should go. This is where lower bound and upper bound become more useful than plain equality search. Lower bound is the first element greater than or equal to k, while upper bound is the first element strictly greater than k. Together, those two boundaries describe the whole block of duplicates. Visually, we stop thinking about one target cell and start thinking about the boundary where a condition flips. That shift is important because it prepares you for more advanced forms of binary search. You are no longer just hunting a value. You are locating a transition point in an ordered space. That transition point view unlocks binary search on the answer. In many problems, there is no sorted array at all. Instead, there is a monotonic predicate. Below some threshold, the answer is impossible, and at or above that threshold, it becomes possible. You can think of this as searching over a monotonic function, or more simply, as searching over a yes or no test that flips only once. Imagine shipping packages within D days. If a capacity of 15 works, then capacities 16, 17, and higher also work. Feasibility flips from false to true exactly once. Binary search can find that first true capacity. This pattern appears in square root problems, production rate planning, minimizing maximum load, and many interview questions. The big recognition rule is simple. If the space is ordered by a yes or no test that changes only once, binary search may apply. Why does binary search run in logarithmic time? Because the active search space is roughly halved on every iteration. After one comparison, n candidates become about n over 2. After two comparisons, n over 4. After k comparisons, about n over 2 to the k. The process stops when that quantity falls to 1. Solving that gives k about log base 2 of n. That is why 1 million items need only around 20 steps. This is not just faster than linear search. It is a different growth story entirely. Doubling the input does not double the work. It has only one more comparison. When you internalize that geometry of halving, you start to recognize binary search not as a memorized loop, but as a strategy for collapsing uncertainty at exponential speed. Binary search has earned its reputation because small mistakes are easy to write and hard to notice. First, it fails on unsorted data because the direction choice becomes meaningless. Second, midpoint arithmetic can overflow in fixed width integer languages if you write low plus high divided by 2 naively. Google's binary search bug survived in production code for years for exactly that reason. Third, off by one mistakes can create infinite loops. A classic example is when your update rules allow low and high to stop moving when they are adjacent, so the loop never terminates. Finally, different variants need different interval conventions. Inclusive bounds, half-open bounds, first true, last true, lower bound, and upper bound are siblings, not identical twins. Copying the wrong template is often enough to break correctness. Let us finish with a small problem lab, because this is where binary search really becomes useful. First, consider finding the first occurrence of 4 in a sorted array with duplicates. If the midpoint is 4, you do not stop. Instead, you record that midpoint as a possible answer and keep searching left, because an earlier 4 may still exist. That is the key change. Equality no longer means done. It means maybe, but keep shrinking toward the boundary you care about. Second, consider integer square root. Suppose x is 27. We are not searching for a value that equals 27. We are searching for the largest integer whose square is still at most 27. That turns binary search into a last true problem. If mid squared is small enough, mid is valid, so we save it and move right to see whether a larger valid answer exists. If mid squared is too large, we move left. Third, consider the shipping capacity problem. Here the search space is not an array of data values at all. It is a range of possible capacities. For each capacity, we run a feasibility test. Can we ship everything within D days? Once that test becomes true, it stays true for every larger capacity. So this becomes a first true search over the answer space. These three examples look different on the surface, but the underlying discipline is the same. Decide what boundary you need, choose the predicate that describes it, and then make every update preserve that meaning while the interval shrinks. That is the real shape of binary search. I hope you like this walkthrough through binary search. Stay tuned for more videos where we unveil concepts with clear reasoning and great visualizations. Thank you for watching.